Hi, today we'll discuss Wurtz reaction, one of the very important reaction of the alkyl halides, right? So I just start here from the scratch. There the 2Rx on treatment with sodium in dry ether, that gives R in R plus 2NaX. This is a kind of coupling reaction. Here the alkyl group is coupled and the main product is here this coupled alkene. Coupled alkene is the main product, R in R. Especially for this purpose only, this reaction is performed. Okay. Let's take here one other example. We take here CH3CH2Br, 2CH3CH2Br reacts with sodium in the presence of dry ether. Sometimes dry ether given, sometimes not given. Here main product is CH3CH2 CH2 and CH3 butane, and certainly 2NaX. This one is N-butane is the coupled one. That is the main product. That one is major product of this reaction. It contains two carbon atoms, ethyl bromide. Coupling takes place. Now it is ethyl part gets coupled, doubled, and we get N-butane. In addition to this N-butane, some minor products are also observed, and these are CH3CH3. Corresponding, this one is ethyl bromide. So its corresponding alkane is ethane, and corresponding alkene is ethene, CH2 double bond CH2. These two are minor products. In this case, minor products. Now the main point is here that how this reaction is actually taking place. Right? I just take the mechanism of this reaction. There are the two different mechanistic path of this reaction. One is the radical mechanism, and other one is ionic mechanism. We will discuss here both the part, right? You see. Let's discuss here the mechanism. And that also we discuss here now, radical path of this reaction. Radical path. How this reaction takes place? 2Na means get ionized 2 electrons. These 2 electrons are given to alkyl halides 2CH3 CH2Br, given here the 2 electrons, 1 electron each. Then this one is leaving one of the electron, taking electron and getting separated. As a result of this, we get here the 2CH3 CH2 free radicals and 2Br minus, because 2 electrons, Br is having 1 electron here, but it is retaining, and 1 electron it is taking from this sodium. CH3 CH2 free alkyl free radicals form. How these free radicals interact, that you see. This is the main path of the reaction, CH2 and CH2 CH3. These two coupled. This one you can say head-on coupling. As a result of this, you get here the CH3, CH2, CH2 and CH3. Okay. There is one more possibility in this case, and that possibility you explore, that is CH3 CH2 free radical not having the head-on coupling. This one is alpha, from the beta place this will take this hydrogen, and so this carbon is using this electron now with this alpha one, and as a result of this alkyl free radical, which will be abstracting hydrogen from the beta place of the other alkyl free radical, this is getting reduced, and now you write CH3 CH3. And as this one is losing, so this one is getting oxidized, CH2 double bond CH2. If you see this one, we say this alkyl group is reduced as well as oxidized, right? It is a kind of disproportionation step, and this gives here, in this particular case, minor products. This kind of interaction of these two free radicals are not the most preferred in this case, but as their bulkiness or the steric hindrance on this alpha place increases, this head-on coupling decreases, and this kind of alpha beta interaction increases, where the corresponding alkane in alkene are becoming the major product, right? So we observe here these products. I hope it is clear now. This is the radical path, right? Let's take here ionic path. Okay, let's take here ionic path of the rays. Okay, ionic path. In the ionic path, we take the same thing. 2Na plus 2 electrons. Now these 2 electrons are given to halide CH3 CH2Br. Will accept here the 2 electrons. That will give here. Anyway, you know, alkyl halides prefer to be dissociated hydrolytically, prefer to be dissociated as CH3 CH2 plus Br minus. That will be accepting 2 electrons here, and as a result of this you get CH3 CH2 minus and Br minus. This one, this carbanion This carbanion is the carbanion what forms. It is acting as nucleophile and as base. Can act as a nucleophile, can act as base. And so, you see here, now this one CH3, CH2 minus primary carbanion is better nucleophile, will be attacking on this alpha place from the back side and push it out. This is perfectly SN2 path of the reaction. This one is SN2 path of the reaction. And as a result of this, CH3, CH2, CH2, CH3, and here the Br minus. Br minus here, Br minus there will form 2 NaBr, and this is the main product here. Because in this case, when this one is nucleophilic, this one is primary one, that time SN2 is the main path of the reaction. And as you know, SN2 competes with E2, E2 competes with SN2. The age of SN2 reaction is maximum on the primary one, decreases to secondary, decreases to tertiary, they are almost not possible. At the same time, the age of E2 reaction is least here, but that increases when it is secondary, and it is the best when it is tertiary. So, in this case also, you can write, the other possible one, there the HCH2CH2Br. When this one is acting as a nucleophile, it's okay. But when this one is acting as a base, then this will be pulling out the hydrogen from here. This one is moving here, and this Br is pushed out. This is an E2 path. As a result of this carbanion, which is pulling this hydrogen, is getting reduced, and we write here the CH3CH3, and this one is getting oxidized. Now we write here the CH2 double bond CH2. Okay. You can say here that these two are the minor products, result of E2 path, and this time this major one is the result of SN2 path. Result of SN2 path, this is the result of E2 path. Okay? Let's take here some more examples. Right? You'll understand better. Okay? When we observe this reaction over secondary one like CH3CH, CH3Br, 2Na, we get here the major product CH3CH, CH3, CH, CH3 in this CH3. Yes, this one is still major only. Major product is this one. But as a minor product, we also observe CH3, CH2, CH3 and CH2 double bond CH, CH3. Alkanes and alkenes. These are minor products. Yes, even in this case of secondary alkyl, these corresponding alkenes and alkenes are the minor products, right? You take here tertiary one, 2 CH3CCH3 CH3Br. When that reacts with sodium in the presence of dry ether, whether it is written or not, let's understand. Here we get CH3CCH3 CH3 CH3 CH3. This time, this kind of coupled alkane is, this one is minor product. E of reaction is very clear. This one is minor product because head-on coupling is very difficult. First thing. Second thing, when this tertiary carbanion will be attacking on the beta place, will try to attack on this alpha place, the SN2 reaction is least preferred, almost not possible. As a result of this, there the yield of this one is very less. In the most preferred path is attack of this tertiary carbanion on the beta place, beta hydrogen will be pulled out and elimination is the most preferred. Right? And that's why CH3 corresponding alkane and corresponding alkene, these are major products. This time understand, remember, keep in your mind that these are major. So the Wurtz reaction, where the coupling is the main stream of the reaction, that is most preferred, giving the good yield on the primary, then secondary, then tertiary. Okay? Here we learned some of the characteristics of this Wurtz reaction, right? Let's take. We'll discuss now characteristics of Wurtz reaction, right? Many features are there regarding this reaction that we need to discuss. Okay, let's start now. First point, unsymmetrical alkanes, right? Unsymmetrical alkanes, and or you can say or alkanes with odd number of carbon atoms. Alkanes with odd number of carbon atoms are not synthesized. Why not synthesized? Because this is coupling reaction. So, if that is unsymmetrical, alkyl halide, in this alkyl halide, if the alkyl part is unsymmetrical, on coupling that becomes symmetrical. If alkyl group contains odd number of carbon atoms, on coupling that becomes even. So the normal way you can say, naturally you can say that this kind of alkanes cannot be synthesized. Immediately you will say, sir, if you take the different alkyl halides, yes, questions are also there. If we use the different alkyl halides, that's why you understand this one, that here, but I write here this word. Different alkyl halides are treated in the presence of sodium in dry ether. Then let's take here one example. We take here one example that CH3 CH2Br ethyl bromide and isopropyl bromide CH3CH CH3Br isopropyl bromide. If we take these two in the presence of Na in dry ether, then what happens? True, natural. You write the same product. What you feel? What you feel here? You feel here that these two will become true. We write here one product like CH3CH2, this one, and this one, CH3CH3. This is the product. Sir, this one is unsymmetrical one. This contains here odd number of carbon atoms. True. Then why this statement? This statement is there. If we perform synthesis, it means that product must be in the significant amount. Good yield of that product should come out. Right? Now, this one is very less. Although relatively this is the major product. If the question is like this, what is the major product, what is the main product, we write this on. But this is not in the significant amount, and that's why we don't synthesize this product through this method. This is a major product. What are the other products? Let's take here what are the other products. Other products, for that I tell you here that you see that self-coupling will take place here. Okay? On self-coupling we get here CH3, CH2, CH2, CH3. And self-coupling of that will give here CH3, CH, CH3, CH, CH3 and CH3. Any other product? Yes. What are the other products? You see this one. Here I am telling you. As per that mechanism what we learned, here the CH3, CH2 minus forms. Take this rough work here. CH3, CH2 minus forms. When the CH3, CH2 minus is there, this can attack on the other CH3Br, this one you know, and this is the product. But if this attacks here, pulls out the hydrogen, then this one is CH3, CH3, and this one is CH2, double bond CH2, right? So, other products are CH3, CH3. CH3, CH3, when it takes hydrogen from this beta place, and as this one is losing hydrogen from this beta place, so this one is CH2 double bond CH2. One more possibility is there. This carbanion when forms, this can attack on this alpha, then this is the product. But if this will attack on this beta, there the HCH2 CH CH3Br. If it attacks on this one, then this is moving here, this one is pushed out. So when this will attack here, the same product form, CH3, CH3. But when it attacks here, a new product form, that is CH2, double bond CH, CH3, this one is propene. So other product is CH2, double bond CH, CH3. Any product, any other product? Yes. Not only this carbanion forms, but even this carbanion forms in this process. Negative charge may be there. So you think here CH3CH minus CH3. If that is there, then this will attack on this. If this will attack here, if this will attack here, similar product forms. But if this will attack here, pulls out the hydrogen, ethene forms. In this one is CH3CH2CH3, so a new product forms, that is CH3CH2CH3. This propene is also one of the product this way. And if this one is taking the hydrogen from here, then this one is the propane. This is also one of the way of its formation. And if this will attack directly here, this one is the product. Any other product? No. This time there is one question: which of the following is not the possible product in this reaction? Yes, this is the possible product. This butane is the possible product. This 2,3-dimethyl butane is the possible product. Ethane is possible, ethene possible, propene possible, propane possible, pentane not possible, hexane not possible. Right? So these many products are there: 1, 2, 3, 4, 5, 6, 7. Total 7 products are there. And in that one, this one is relatively major, and that's the reason it is said that not synthesized unsymmetrical alkanes or alkanes with odd number of carbon atoms are not synthesized. Okay, I hope you got it. This is one of the important things, right? Let's take here the next characteristic. Okay. Next one. Here, this reaction, this Wurtz reaction is not successful with arylic and vinylic system. Although the process modification is there, that is called feeding reaction, but in general belief is there, in general understanding, Wurtz could not synthesize coupling of arylic, coupling of vinylic in this process. Right? So this is the limitation. Right? One more modification is there. What is that modification? But aryl alkyl group can be synthesized, combination, coupling. But aryl halides or vinyl halides can have this kind of coupling reaction with alkyl halides. What is the meaning of this? Let's take here one example. Here, chlorobenzene plus CH3 CH2Cl, right? If that is treated in the presence of sodium, in the presence of diether, we get here this cross-coupled product, ethyl benzene CH2CH3. This is the major product. You can have other byproducts also. This one is major. Other products, possible products, ethane, ethene, CH3, CH2, CH, this one coupled alkane of this one. Here self reaction, so CH3, CH3 plus CH2 double bond CH2, right? Even this one is one of the possible product, Benzene, because their carbonyl conforms. This can accept those two electrons, carbonyl form. This will pull out the hydrogen from here, benzene will form. This will attack here, ethyl benzene forms. When ethyl carbonyl attacks on the other ethyl, butane forms. When ethyl attacks on the beta and pull out the hydrogen, then ethane forms and ethene forms, right? There is scope of this kind of reaction, and you know this is the modified one. This is the modified form. Later, it was the Petty who modified this one, and that's why this is called Wurtz-Petty reaction. Wurtz-Petty reaction. This one is Wurtz-Petty reaction. This kind of reaction between aryl and alkyl in the presence of sodium and dry ether is called Wurtz-Petty modification. Right now, okay. This is one of the things what you should keep in your mind. Right. Let's take here one more characteristic, important one. See this one. Here, next one, we think that alkyl halides react with sodium in the presence of diether, and that gives coupled one. But it is not applicable with all alkyl halides. If any functional group is present, that time we have to reconsider this statement. We have to review this one. And for that I write this one. Alkyl halides containing any functional group other than OR alkoxy, NR2, internal triple bond and double bond. OR, NR2, internal triple bond and double bond. Alkyl halides containing any functional group other than these don't give this kind of coupling reaction or Wurtz reaction. Don't give Wurtz reaction. Why? Because other than these functional groups, other than OR, NR2, internal triple bond and double bond, all other functional groups are more reactive than the halogen towards Na. Other kind of reaction starts. There the reaction center is changed, right? That activity center is changed. That sodium will be acting on the other functional group instead of halogen. One of the interesting example I am giving you, because this is very frequently asked and very important also. Remaining reactions you will learn slowly in the different chapters. Alright? I just tell you here, this one you see, this one example. This one is HO CH2CH2Cl. If that reacts with Na, what happens here now? Our OH group is present. This is acidic one, and if that reaction takes place, then this reaction will take place here. This one is the active matter. Hydrogen gas is released, and so this will be O minus CH2CH2Cl, and here the hydrogen gas is released. Right? Hydrogen gas is released. This one is O minus CH2CH2Cl. This is the different thing. That their different reaction takes place further, because the O minus, when it forms, O minus Na plus, when it forms, this is acting as internal nucleophile, and intramolecular substitution reaction takes place, SN2. This will be attacking here on this CH2, and this one is pushed out. Here the product is CH2 and OCH2, this kind of epoxy, sometimes cyclic ether, are the products. It's okay? Reaction gets diverted in some other direction. So remember this point, that if any functional group other than these are present, important, internal triple bond permitted, but terminal is having acidic hydrogen, similar thing will take place, and that's why there this kind of reaction won't be taking place. Okay? Sure. Yeah. The next one, reaction with dihalides, geminal dihalides, vicinal dihalides. Let's take here that. Reaction of Na ether with dihalides, geminal dihalides. First we take here geminal dihalides. What are geminal dihalides? Alpha, 1,1 dihalides. What happens here? First you see CH3 CHCl CO. If that reacts with Na in ether, in the presence of ether, we get here CH3 CH double bond CHCS. Yes, this one is coupled alkene forms. Coupled alkene. That forms. What happens here in this case? You cannot keep this one under this Wurtz reaction, right? But Na ether is there, and this one is one of the competing reactions. Here, what happens that you see that 2Na plus 2 electrons. These 2 electrons are given to one of the halogen. So CH3CHCl plus 2 electrons. Immediately carbanion forms here. You get here the CH3CH and Cl minus. Immediately this one, as this alpha is having one more Cl, that is also lost, and that will give now CH3CH minus plus. This is carbene. Carbene intermediate forms in this case. What forms in this case? Carbene intermediate. In here, mainly we are dealing with singlet carbene. Mainly we are dealing with singlet carbene. This is a carbene CH3CH, and this one of the orbital is vacant, one of the orbital is occupied. There the coupling takes place. CH. These two orbitals are interacting. This filled with that vacant one, this vacant with that filled, and as a result of this we get here CH3CH double bond CH3. Yes, this alkyl forms. Understand this one. This has the different course of reaction. In this case, carbene is the intermediate, right? CH3CHClCl. This 1,1 dichloroethane gives here coupled alkene, and it's not limited to this one. All such geminal dihalides can give this kind of product. For example, if this one is CH3CH3Cl in there, the Cl. If that reacts with Na in ether, yes, they are also same thing. CH3CCH3 double bond CH3 in there, the CH3 alkene forms. Not only this one, if you take here the cyclic also, yes, Na ether will give here this a kind of coupled product. And the very interesting thing is this one, that in this case there is no difference in between the various halogens, whether you keep here the same halogens or the different halogens. Course of reaction will be same. Even if I take here PH CH Cl in there the Br, if that reacts with Na in ether, yes, product is PH CH double bond CH and PH. Here in most of the cases when I say dihalides except fluorine, you can take chlorine, bromine, iodine, right? In any way you know, there the diiodides are extremely unstable. So mainly it is all about the chlorine and bromine, and no difference in writing products. Okay, what we have seen here? We have seen here geminal dihalides. How geminal dihalides respond to Na in the presence of ether. Now we'll take here vicinal dihalides. Okay, let's take here vicinal dihalides. Reaction with Na in ether with vicinal dihalides. Vicinal dihalides. Okay. What happens if vicinal dihalides? Let's take here one example. Cl CH2 CH2Cl that reacts with Na in the presence of ether. What happens? Here alkene forms. Corresponding alkene forms. How? That is very important, that how. Let's take here, there the 2Na plus 2 electrons. Now these 2 electrons, there the Cl, CH2Cl. 2 electrons are given. Immediately carbon forms. We get Cl, CH2 minus Cl minus. Here the even Cv kind of reaction you will observe. Here there is carbon, and so this one immediately moves towards this one, and this one is pushed out, and we get CH2 double bond CH2. Everything. It happens the same way. Even if you take here the other one, like 1,2 dichloro cyclohexane and A ether. Yes, same product. Cyclohexene is the product. Carbon intermediate. That forms. Here on this pattern only, this one, although we are discussing here vicinal dihalides, on this pattern only other dihalides react. For example, if you take here 1,3 dihalides, if you are dealing with 1,3 dihalides, then that will be giving here in the presence of Na in ether. That gives cyclopropane. Cyclopropane. Take it. Cl, CH2. This is the orientation, right orientation to understand. Na ether, 2Na plus 2 electrons given to this one, their carbanion forms. You get here Cl, CH2 minus Cl minus. This will be attacking on the third place, and the product is CH2. Cyclopropane. Yes, that's a product. Here, reaction in between the first and third is appropriate only. 1 and 4 is not appropriate. That's why this kind of reaction is least observed in the case of 1,4. But again, similarly observed in the case of 1,5. Cyclobutane is not the expected product in this case. It's not observed if we have 1,4 dihalides. No. But 1,5 dihalides, 1,5 dihalides will give here the cyclopentane. Most of the cyclic compounds for annulation, cyclization, this kind of reaction is performed. 1,5 dihalides and Na ether will give cyclopentane. 1,6 dihalides will give here cyclohexane. Here it's not exactly 1,6. You can take this in wider sense, maybe substituted. That time cyclohexane derivative you will get. I just discussed few examples You will understand this better, okay? Here you see. This one is Cl. If that is treated with Na in ether, earlier there was one question in the IT that instead of ether, Na was given in the presence of dioxide, that is also high boiling ether kind of solvent, dioxide. This one is that one. This one is what? 1, 2, 3. This is 1, 3. There carbon forms and that will be attacking here. This one is lost. And the product is this bicyclic product, bicyclic. Interesting point is this one, as I mentioned it earlier also, whether you keep here the same halogen or the different one. Na ether will give the same product. Na ether will give here the same product. You can take here some of the reaction like this. If this kind of compound is treated with Na in the presence of ether, yes, notice this one. This one is 1, this one 2, this one 3, this one 4, this one 5, 6, 7, 8, 9, and 10. This one is 1, 6. Dihalides, same thing. One Cl is lost, negative charge will form, that will move, and other Cl is pushed out. And the product is this kind of bicyclic compound. It is not limited to this one. If this 1, 2 dihalides, understand this one. 1, 2 dihalides. If we get over the benzene also, there we have Cl or the ClBr dihalide. If that is treated with Na ether, important, okay, what forms? You know this one here, the triple bond will do. Benzene forms. Here, benzene forms. This is the benzene intermediate. Benzene intermediate forms. If there is nothing here to absorb this intermediate benzene, then there the self-coupling takes place. Then this will be giving here this kind of coupled one. This kind of product forms. But if this one has been given with, just I am telling you, there the CH2 double bond, CH double bond, CH2 in the presence of Na ether, this is diene which is capable to absorb this benzene. Then that kind of coupling won't take place. Benzene only forms. First benzene forms. This benzene, what forms? That reacts with CH2 double bond, there the CH double bond CH2. And this kind of diels-aldol reaction takes place. And that is giving finally another cyclization, double forms. Interesting reaction. If this one is treated with selenium in heat, this is giving here naphthalene. This is used for that kind of synthesis. I hope Endless examples are there. Endless examples are there. In NA-ethane is used for many good purposes, for many different syntheses. But here I have discussed some of the selected reactions which are more frequently asked and more important. I hope you got it. Thank you. Enjoy.